Hi, everybody. Thank you for joining us today on Runspace Workflows. Parallelize your code one step at a time. Very big surprise, we're going to be talking about parallelization here quite a bit. I'm Fred, Cloud Solution Architect at Microsoft, where I'm doing security automation and other automation and more, well, mostly PowerShell for the company. You can reach out to me even after this conference, best reached under the PowerShell Discord, named Fred. I'm a mostly silent observer, best if you ping me. Usually I hang out in the PS Framework channel, but well, yeah, just reach out to me at any time. I'm always happy to talk about all kinds of things, mostly PowerShell, especially in particular when it comes to bragging about my toys, which is, well, a professional risk when you encounter me at any place in the world. Other than my bed, but that's a different story, and we would be having some other words on that topic. This session is going to involve quite a bit of set toys, specifically PS Framework. So this is the link list you might want to do a quick photo of if you want to be sure you can follow up on everything. All the presentation materials will go live a few minutes after this talk. So if you want the demos to play around with what you were seeing, that's where you can grab them under my GitHub repository. P224-PowerShell Summit Runspaces. So, yeah, what are we going to talk about? First of all, I always like to give some context and establish the problem that we're trying to solve. So we will be looking at the different patterns, how we parallelize in PowerShell. Some of them are going to be rather well-known patterns. Some of them might be surprises you didn't think about before. We'll find out. And most notably, we will point at a major problem that I'm trying to solve. Then we are going to solve it. And we're going to do it without any dependencies, none of Fred's toys involved. Something you can do and just plugs in somewhere, because as much as I dislike that part, but it is just a reality. Not everybody can always just grab the latest huge kit of toys from Fred and use them. There's the security thing, they want some review. Maybe there's an organizational process that says first you need to get an approval process that cannot possibly be completed. Sometimes we just get a no, you can't. So we will try to solve this problem as best we can just with the built-in PowerShell tools. And once you fully grasp and realize what kind of pain is involved with that, I'm going to be bragging about some of my toys. All right, parallelization. What are the usual patterns that we're seeing? One of the greatest and simplest one is inline expansion. Let's say I have a set of commands I pipe from one to the other. And if I now want to parallelize one of those steps, that is fairly simple since we have PowerShell 7, because this is more or less the domain of for each object -parallel. It's simple, it's not optimized code, just a simple proof of concept here. But this allows us to, well, parallelize one step in the pipeline. The key advantage here really is it is absolutely simple. It's as easy as parallelization gets. There are open source modules that provide that feature also in Windows PowerShell if you can't go to PowerShell 7. So yeah, can be done. It's fairly easy. There's just one major problem here, and that is while it is simple to use, it is very hard to fully define the context and provide resources and plan out the whole thing. Like, the number of controls we can tweak is very limited in the setup. Also, it only works inline in the pipeline, so it must be done by the end of the pipeline. And sometimes fire and forget and fire and come back later is a feature we would like, and inline expansion does not offer that. Which is, well, when we go jobbing. Let's say I've got a server I want to run a script against. Simple enough, just like one task sequence that I'm doing. And if I now have 100 servers, I run this script 100 times in parallel and wait until I'm done. And if I've got a management solution, something a bit more complex set up, well, I can do something before and after and just tie that whole thing into the workflow. This is still simple enough to set up. We have posh-rs job, we have start threads job as a built-in feature in PowerShell 7. And let's be honest, putting together a quick custom Runspace setup is well enough documented. We have a dedicated session on that. I think it was yesterday. So setting up some Runspaces is something we can do quick enough to get the same effect. So far, that's nice. This, however, has usually one problem, and that is for the entire sequence of that job. Well, that is one thread running in parallel. And there might be some problem with that. We'll be coming back in a little bit when we come to the problem description, because this is what we're going to be expanding upon. But before we do that, let's talk about the Highlander Runspace scenario. Let's assume I've got a module, and there's something I want to have running in the background. So I spin up a Runspace that's just going to do its thing behind the scenes. This can work really well until somebody takes my module and also sends it in multiple Runspaces, because now each of them is going to spin up one of those background Runspaces. Now imagine that background Runspace we're implementing later gets an update where it uses the module that is spinning up the Runspace. Oh, we've got an infinite loop of Runspaces being spawned. Yeah, so we have a scenario where we want to have a unique Runspace per process that cannot be duplicated. We can try to solve this by looking for a Runspace name. We can name Runspaces starting PowerShell 5. And I dearly hope none of you needs to go back to older versions. I know some of you still will anyway. Sorry, my apologies, my condolences on that point. Still, we can look for the name, but that still has us the race condition. What if we spin up multiple Runspaces at the same time and they do the check in parallel? All of them don't find that Runspace yet, and then decide to create that Runspace. The name is a decoration. I can have multiple Runspaces of the same name. So there is some problems to be solved here. We are not going to be talking about that particular scenario, but if you ever need that kind of capability, PS Framework does have that. Mostly because I needed it for my own logging. Otherwise, we would have that, oh, I'm trying to access the same file twice in parallel problem. So that's how that works. We can then submit data to that as one of those scenarios. Or what could we use for a background Runspace for? For example, we could be using it as a cache refresher. So the background Runspace keeps data in a cache up to date, and the main Runspace directly accesses that data for ease of access and no delay. That's, for example, something happening in DBA tools to provide up-to-date tab completion. We don't want people to have to wait for that, but we also want to have some control over that. So in DBA tools, there's a background Runspace handling the cache refresh. Another thing we could be doing is sending workload tasks and then have the unique main Runspace act as a task scheduler kind of thing, which incidentally is the other pattern that I occasionally encounter, where we have a task manager Runspace that is supposed to be a unique Runspace, and other Runspaces submit tasks to happen whenever we want to do it, either on a schedule, or I've got a main Runspace that wants to clear out some temp data. I've got a module that needs to purge some temp things. I don't care exactly when that happens. I don't want to wait for it to complete because it might take some time. So I'm going to just, well, throw this to some job manager for me, so I don't need to implement my own full, well, Runspace thread just for that. So we could have some criteria, some scheduler, and some prioritization, who is one time. There's a lot more effort we could invest in that scenario. If you ever have a need for something like that, again, PS Framework does have something here. I must admit, one of the more underutilized features. So I mentioned the problem. I've got this nice script that I want to parallelize. The problem is now this script isn't not necessarily something I want to run against hundreds of servers. And this script, well, actually, it is composed of several different tasks or steps that I take within that script. Now, what happens if I have different parallelization requirements for each individual step? Let's say I can do the first thing 3 times in parallel before I'm being throttled to death by the API. Now the next one has a lot more capability. I could do this 10 times in parallel, and each step here is taking a lot more time per item than the step before. So having that scale up to more parallel executions would be beneficial. The next one can only be done once. Then we have one with maybe where 5 times in parallel could be a thing. So each step could have different requirements here, also different requirements for the context we need to provide, the resources, the tools. And, well, we could be doing 8 separate jobs here and have them have different throttling limits. That would work. Now there is one problem. Let's assume our step 2, which you do 10 times in parallel, usually is safe to run 10 times in parallel. But depending on what input it receives and in what format, it needs to do more requests per items, and suddenly we run into throttling. Now we have a need to coordinate those 10 jobs that are running in parallel. We have a need to coordinate between them so they don't actually run into that problem. Or let's say I have step 4. With step 4, I'm trying to do some graph API calls. And in order to avoid throttling here, because this is a particular nasty API subset of that, I want to use different accounts for each of those 5 run spaces. So I've got separate accounts, even though they're basically doing the same thing. So I need to provide different values for that. And then there's this last problem. When we have the traditional job set up, we have to wait for a job to complete to collect the results. Now let's say one of our jobs is get mailbox from Exchange Online. This is perfectly safe to run in an environment with 1,000 mailboxes. Now assume we have 1 million mailboxes. At some point there's this nice, friendly, red-colored text going to show up out of memory exception. Or your infrastructure team is going to have some nasty words for you if you're asking for that particular mega server to be able to run the script. So we actually would like to have a capability to pass data through these steps before the job completes, which is going to lead to a few interesting questions. For example, how will any individual step ever know that it is completed, that there's no more data coming in? It's a background run space basically waiting for the next item input, and is the step before that just slow and something is coming in? I mean, the step before might have been throttled to wait for 3 seconds. 3 seconds can be an eternity. So how does any step know, okay, I'm done? So there's going to be some problems here. Let's take a look at the tech side. So, all right. Mouse, it's your turn. There it is. So, we have, thank you. That makes it a lot easier if you actually are able to see something. So I have some preparation here, a custom invoke runspace command. We are not going to be investigating the code. That's a few hundred lines of script that don't fundamentally change the way what we are talking about here. It's a way to, well, set up runspace actions happening and provide context. As mentioned, we have a session about that. You will have access to all of that code to look that up. Just trust me, it's going to run script logs in parallel in a background runspace. From a fundamental design perspective, how do we create run spaces? Well, we start with an initial session state. What the hell is my Runspace supposed to be able to have access to? What commands, what modules? Then we add more contents here, like custom variables. Come on, there we go. Functions or modules or whatever else we want to pre-provide. Then we define a Runspace pool that basically handles our throttling. How many executions do we have in parallel? We define run spaces, as many as we want, assign them to the pool and kick them off. And at some point, we just have to wait until they're done and collect them. It's a bit nasty, very .NET type heavy code. So feel free to investigate that. We'll have that covered for you for now. There is also a pretty good blog post I still like to reference for setting up my first Runspace from Chris Lemaire. It's from the year 2016, but it still works the same way today. So if you want a more guided tour on how to set it up rather than looking at thread code, which is admittedly not heavy on comments, you can go there. So let's do the first thing. In order to make this properly work, we want to exchange data with queues. A queue is a kind of array or collection where the first item that was inserted into it is the first item that is taken out of it. So when one step in our pipeline provides output, we write that to that queue, and the next step would then read that from the queue. For that first, we have here one problem that we need to solve, and that is the get mailbox conundrum. Get mailbox will return all of the mailboxes, but if we wait for it to complete, our memory is going to burst, or at least we have to assume it's going to happen. So what I do here is a quick demo on how we can catch that by using a command that is going to return whatever number of items I want, and it's going to wait 1 second in between to simulate a long-running command that keeps outputting some data. The second command to showcase the whole thing is write input, which is taking input from the pipeline and then just writing it on screen, which is going to show when exactly it received that item. So, as we can see here, the second command in the pipeline did not wait the full 5 seconds for the items. It wrote it 1 message per second. In a PowerShell pipeline, command 1 sends to command 2 an object. Like here, we produce output. At this point, the process step, or the current step in this command is going to be on hold until every command afterwards in the pipeline is done. And then, only then it's going to continue. So, if we now, instead of write input, have a for each object and add that item to a queue, we are adding mailboxes to that queue as they arrive, rather than having to wait for the command to complete, or whatever else slow gathering command API request we're doing. So we need the next construct, which is a queue. As mentioned, first in, first out. We have different types of queues in PowerShell in .NET. We are accessing the .NET types for that. And there's a namespace called concurrent, which is intended to be thread safe. So we don't have any conflict with one or multiple threads or run spaces adding data or removing data. So let's add that. To add an item to it, we just use the enqueue method. They're now in there. And to remove an item, we need to do try the queue. This is a bit of an annoyance because we first need to declare a variable to be filled in. And once we have that, we can use that with the ref typecast, which means that method call is now going to fill in the content of the $result variable. So this is not actually an input. It's only a .NET method call that has 2 outputs. Because what it also does, it returns $true, whether something was successfully dequeued or a false if not so. Otherwise, we would have trouble figuring out the difference between there was a null value in the queue or there was nothing in the queue. So we now have here the value number 1. If we now dequeue the next item, we have here value number 2. And now there's nothing more to dequeue, so we get a return value of false. And the result has also been cleared. By dequeuing an item, it's not only read, it's also removed from the queue. So let's create a new concurrent queue. And I'm now going to invoke Runspace with providing the variable of the queue, the processing queue. I'm also going to provide the function getDataSlowly, throttle 1, so only one runspace in parallel, and the invoke Runspace expects at least one input, and for each of that it's going to try to set up a runspace. Since we only have one long-running runspace, which is going to do 30 times getDataSlowly, and then add that to the queue, we ignore the original input actually. So that's okay. So get that started. Start that job. And the second job is also receiving the same parameters, the same queue, and is going to try to dequeue an item, and it's going to wait until done. It also knows, hard-coded here, that we expect a total of 30 items. So it knows when to stop. And then we finally produce the result. Fire. We now have 2 separate jobs. And at some moment there was one item in there, but the second step runspace is picking it up immediately, since it is faster at processing data than the first job is at generating data. And if we're done, we can just wait for it to complete. And once that method call is done, the job has completed. The second one returns actual output. So it's all there, and we have all the items that the second one produced. And that is how we were able to pass through information from one to the other. Now this has obviously a major problem right now. We need to know ahead of time how many items. Otherwise the second job would never have known, I'm done, I need to do something. So how can we solve that? So the first thing we can do is we can declare we are done. There is also a nice thing called a concurrent dictionary. That's basically a hash table, only it is able to have read and write in parallel. So let's do that. And we can basically use it the same as we would a hash table. So we set up one of those as our status flag, like this is our current processing state. We have again the queue for the input-output for data transfer. And we now provide both variables to the tasks. So now status is going to say, I'm good, once they're done. Once this task is completed, it's going to set this flag. We're good. And the second one is going to continue until the status.input has been set, and then it's going to break. Since this only happens when it fails to dequeue an item, it is still going to process the last item we queued before that. So we don't have really a risk of missing out anything. So job 1, job 2, they're still as boring as ever. Still getting sometimes items. And we can now wait for that to complete. And they actually completed successfully. Otherwise, it would have hung until done. So that's nice when we are able to actually correctly have a status flag like this. Problem here is, well, sometimes we still need to have some processing capability, some ability to count how many items were processed and pass that on. And for that, we need a thread-safe way to update a count. You know about, I've got this number. I'm going to increment that. Fred, do the spelling correct. And if I now access that, +1. Problem is that this default incrementing is not thread safe. There's an annoying way to do this in C#, which is why we have about 20 lines of C# code in here that implements the type for us. So I'm going to dump a large set of random numbers in this command. We are going to set up queues to exchange information. We also have a final result queue, status transfer, and an incrementer that we're creating. And of that, we just pass through some parameters to our run space. Now here's the thing. I managed to mess that one up, accidentally hitting that part. All right. We are now invoking the first run space and 3 times in parallel, but we don't even know how many that's going to be. There's no way we can say, okay, I am done, because each individual task action in there doesn't know whether it's the last one. So we instead increment by 1. And the second job is going to, well, it's going to try for some done, but the status doesn't, the first step isn't going to update the status to done. Instead, what's going to happen at the bottom, once we kick those 2 off, is we first collect the first step until it's done. We know when it's done because that is going to end once all the items are being processed. And while our incrementer count is greater than that count, we are waiting. And once this is completed, we now know that all the items in the final result queue that the second step produced have the exact same count as the first step was actually incrementing. So it has now processed all the input from the first step. So we can now set this to true, collect the job, which is going to happen immediately, and our results correctly reflect this from a processing perspective. Which leaves us the next problem, throttling. How the hell do we throttling across multiple run spaces? Well, we have a few lines of C# code that we're not going to go into here, but they will compile without dependency. It creates a throttle object, which we can then add a limit how many executions per time. Did I mess that one up? Yes, I did mess that one up. No. Okay, I set a limit 3 times per 10 seconds. And whenever I now call the getSlot method, it is going to increment the count of slots. And once we hit the limit, it is going to wait until the first ones have expired. And you can call that for multiple run spaces. We can also add a second limit, in which case both limits apply. No more than 2 calls per 5 seconds and no more than 3 calls per 10 seconds. Now we have to wait on the third call already. And after about 5-ish seconds, including the delay Before that, we get the third slot. Now we run into the second limit, and we're good. We can also do a hard timeout on this thing. Like sometimes we have a REST API that says, hey, wait for 10 seconds before you call me again. And with this not before call, we can define that. And now it's going to wait 5 full seconds until we're done. All right. We can provide that to a background Runspace as a variable, same as all the others. And then have that executed and call throttle.getSlot on each time we do that. Here's a new one, parameter. If we specify the wait parameter, invoke Runspace is going to block until it's done, and then result the results at the same time. So it's basically the same as the calling the .collect method immediately. Yeah. There we are. And we can see the time jumps between start and end when we hit the throttling limits. So that was respected. Okay. This is how far I'm planning on going with doing the custom part. There are a few more considerations. You can look that up in the docs. I've got more examples to run through things. But you know how it is. I can't really end a talk without bragging about my toys. So we're now getting to the part where we get the comfortable features and don't have to do it all ourselves with some finicky, well, manual creation. All right, what we need for that really? PS Framework module, which implements the whole thing. This feature, amongst many others, is properly documented. And I totally did not forget during my prep to input the actual link to the specific Runspace workflow documentation that we're about to see. But it has a landing page under documentation, PS Framework documents, Runspace Workflows. So fundamentally, Runspace workflows have 3 components. We have the overall workflow, which is basically all of the things, the entire timeline we saw before with the individual steps. We have workers, which is the one step in the workflow that we're defining, where we can say, like, do this 5 times in parallel, do the throttling, do whatever we needed to do. And we have automatic queue management, so we don't have to worry about that. It's doing that for us. So let's set up a basic workflow. I create a new workflow object, which is the container where everything goes in. Once I have that, I add workers to it. The first one is going to take whatever input I define as input by the name, and the result objects are going to end up in the queue named processed. This is going to work as the input for the second worker, which is going to write the results into the done queue. The first step is going to happen 3 times in parallel. The second is going to happen 2 times in parallel. The input that we will provide later is $_ within the script block, and it's going to be created here. Processed is going to have the value ×2, and finally we'll be updating the result with multiplying against by 3 in the second step. Simple mathematics going on here. Nothing particularly weird, I hope. Then we add the values. At this time, nothing has happened yet. Nothing is started. We're now adding 10,000 numbers as input to the input queue on the workflow. And then we start it. We can wait for it until the queue done has 1,000 items, and then we clean up so the run spaces don't linger around after we don't no longer need them. Since we don't have any throttling in there, this just ran through and was done, since doing simple in-memory number processing is quite fast. We can then use read PS of Runspace queue to get the result that's in that queue. We can, however, also take a look at the workflow object. We can see what queues exist and how many items are in there. collect that. Finally, clean up the entire Runspace workflow. We need to do the remove step also, even though we already stopped the run spaces, because PS Framework is going to cache all the Runspace workflows in memory until the final removal is done, in case we forget about storing that in a variable. Otherwise, we would have no mechanism to terminate the run spaces if we forget to handle that. So we also have this final removal step necessary. And that's our result. We've got 1,000 results, and the numbers are correct mathematically. As usual, when we do work with run spaces, the order of return value is not guaranteed. So that's okay. We are, however, back at the position where we need to know the numbers. And that's a bit of a problem. So what we have here is a concept of closing a queue, when we know that nothing is ever going to happen to that queue anymore. And with that, we can declare this is done. So I create a new workflow, and I add to the input queue 1,000 items, and I'm telling it, you're done. Nothing is ever going to be added anymore to the input queue. And now, we do the same thing again. There's a bit of a sleep involved here, but close out queue. The worker is going to launch 1,000 times, or it's going to keep launching items here until it no longer has any item in the input queue. And then it's not going to sleep, because it can know through that line that there's never going to be one more input. So once it has done its final task, it can state, okay, I'm done. I will never ever get another task to do. So it can then go ahead and continue this I'm closing a queue thing to the next step and close its out queue, because it is never going to write anything anymore to that queue, because it's done. It will no longer receive any input. And the same we can do with subsequent workflows and workers. This one is also going to close its out queue when it's done, which is the done queue. And now we can simply wait until the result queue has been closed, or the worker name result has closed its out queue. And unless I messed up my demo, we now have all the items. Demo gods, thank you. Okay, now this should have been 1,000. The code and I will have a conversation after this one. So far, so simple. Just getting something done and flagging it as it's completed or it's not completed. Watching for that and hopefully not encountering one of those worked all the time until I'm trying to present it, the issues. How can we provide resources here? That is mostly rather simple. I define a new workflow. I provide a variables hash table and pass that in as variables. It's otherwise exactly the same code. So I'm not going to have us run through that too fast, too long. We're going to kick it off, wait until it's completed, and clean up everything, and there's our results. Again, order somewhat questionable, but otherwise it worked. If we want variables per run space that differ depending on which run space we're working in, it works pretty much exactly the same thing. It's only that we are providing the variables hash table to the var per run space parameter rather than the variables parameter. The individual variable multiplier should have as many items in there as an array as we have threads that are working in parallel. If we have less than that, the last workers that grab their item are going to get a null value, which is probably not going to lead to very mathematically correct multiplication. If we have more than that, any extra values are going to be ignored. But otherwise, it's the exact same thing. So we are now going to multiply, doing the math here to demonstrate that part. And 20 values, run it and wait. And once we're done, and collect the info and remove the run space, we should theoretically have had something here. Okay. Demo gods. Why did I mess that one up? Workflow object, no results at all. We're producing the item, however. It also was too fast for that, actually. Let's try the whole thing in one go again. Now we have a wait period that is appropriate. And now we have the results. I probably forgot to actually add the worker. So there was nothing to wait for. So far for adding variables, there is a bit more complicated issue, and that is adding functions, commands. If you're adding that to the background run space, we need to provide the variable, the command, of course, get random number, and we now need to provide the code to it. It is again a hash table, expects on the left side a string, on the right side it expects now the source code. Problem here is the way I'm doing this, I'm just giving it the code as a string, and this code is going to be run by PS Framework in the background. So if you now have a secured environment where you allow PS Framework, any attacker could use an untrusted code of an untrusted function. Since this is going to be transported as a string, this function would be loaded as a trusted function in the background. At which point, well, you would have an escalation of, well, code trust, which we don't want. So if you have to work with secure environments, don't provide a string. You can also provide a script block of the function. In a constrained language mode environment, even if you set PS Framework as trusted, it is going to reject any string-based function definitions. It is only going to accept a script block, and that script block must be trusted. No constrained language mode script block. So we've got those two. Define that. Add the Runspace worker, which is going to call the function. And it's done. Remove it all. And finally, we have our results. So this is how we could create this whole thing if we know that our function definition is actually safe. Modules, same thing, same story. We just provide the module name, module path, whatever, depending on whether we have an explicit path or it's an installed module, and it's going to be pre-provisioned. And go. There we are. Next, we have this scenario. How the hell do I implement this with, if I've got one long-running command as the input? I don't have any actual input values. I've got this get mailbox that is going to return 100,000 mailbox, and I need to process them as they come in. We have, again, a slow command to simulate this. And provide that. And in this case, we pipe the result of the command to write PSF Runspace queue. This is going to be a bit more user-friendly for the next part. This is because of how the parameter sets work and how the command resolution happens, which is why I need to explicitly bind them to null. That one's going to be more convenient. And here's one more parameter. If we want to stop the Runspace workflows, even if it didn't complete, what happens behind the scenes is that we are waiting until the current item is completed, and then just don't process more items on the input queue of a worker. Problem is this doesn't complete. It's going to wait until it's got all of the mailboxes, all of the numbers, all of the anything. So for workers that we can't wait for, we need to set the switch kill to stop, so it's then going to just kill it. Again, with some subsequent call, adding some items here. And then we can start the workflow and can theoretically watch the items as they happen. I did test all of the bloody demos, sorry, my mess up. Yeah, there's a few more details there. Any questions about this whole thing? Anything you want me to go more deeply into?
With the PSF Runspace commands, if you're using them inside a module and you need to run commands from that module, especially for private functions, how easy is that?
All right. To repeat the question, let's say we're using Runspace Workflows inside of our own module to parallelize something, and you want to now access commands from that module, especially non-public commands from that module. How easy is that? How non-easy is that? Actually, it's mostly doable. What you need to do in that case is you want to reference two modules. Once your PSD1 file as a path, and then your PSM1 file as the path. That way, first we will load the PSD1, including things like types to import or whatever else you need in the background run space. And then we do the same thing with the PSM1 to ensure you've got access to the public commands. The alternative to that, if you have a problem with doing the dual import because your module is doing something during the import and you would be doing that twice otherwise, is you could instead do an in-module invoke of your command. You can run non-public commands inside, from outside of the module. The way to do this is, let's say, what module do we have here? Currently loaded. Come on. There we go. Let's take PS framework here. I can use the call operator and define a command I want to run. What I can also do first is use getModule and the command name to specify the context in which I want to run this. So if I now, let's do something simple. I'm just going to search for all commands from the module PS framework. It is now going to give me the list of all the commands, including the non-public ones. Well, as soon as it's actually doing something, there it is. Now, this also, for example, includes a write piece of config file, which is not a public command. It's an internal one, which is something I can detect here because of the casing of the command. Otherwise, I couldn't remember all of them. And with that, you could instead have here any internal commands, and they would run. Any other questions? All right. In that case, let's continue on with another aspect that we have completely ignored so far. And that is sometimes we need to do something only once per thread. Let's say I need to connect first, then do all of my executions, and finally, once my step is completely done for each of the iteration, I'm closing this. Let's say I have a worker that receives 1,000 input items. I don't want 1,000 times to connect to Exchange Online, do my thing, and disconnect again. PS Framework workflows have that handled by having begin, process, and end blocks that I can also provide to the worker. With begin, script block is the equivalent to process always, and end. Since I don't actually have a SQL server at hand to demonstrate that, this is more like for reference, an example on how that would work. If your worker says, I'm going to execute 3 times in parallel, it is going, for each of these 3 parallel executions, going to do the begin first, then do all of the actions needed, and it's going to do the end. If you run stop PSF Runspace workflow, it's also going to wait for the last process item and going to the end. So you don't leave any hanging sessions open there unless you have the kill to close switch set. To pass variables between them, as you can see, you will need the global variable prefix. You need to specify this in the global scope because they otherwise don't see each other. Throttling. Throttling works mostly the same way as you see here right now, because I literally extracted the code from PS Framework, which is why this was a bit more lengthy from the total code. We have a command called new PSF throttle, which is going to give you exactly the same object you previously saw as C# code that we didn't go into. It's working the same way, and we've got a parameter to apply this. So in this case, the first command is going to run unthrottled. The second one is going to apply the throttle, which says only 5 per 3 seconds. And we add 20 items that we want to do in Q1, which is the input queue. Then we execute everything and wait until it's done. And we will be seeing all the throttling timestamps that applied that rule. I hope. Step completed. Collect the data, remove the Runspace workflow, and here's our results. And we can see that the first items were basically created, spawned immediately. There were no throttling involved. The second stage, however, after 5 items, decided to wait because we ran into the throttling limits. Wait until works exactly the same way we saw before. If the not before, the problem is our parallelized code needs access to that, and we don't have any $throttle variable passed in. We could be using that, but there is also a way around that, and that is you have an automatic variable in the background Runspace representing the worker, which has the throttle, and we have the not before property. And that's going to, again, have us wait until the not before has expired. Completed here. Got the results, and we have that one 10-second jump in between where we had the not before. And, well, that's it. That's pretty much the run through the Runspace workflows, how I designed that. Any questions? Anything you want to see? Shall we have a few more minutes? Well,
your earlier example of using the queue as status message, didn't you still have a race condition in that?
do we have race conditions when previously when we manually set up the queues and the status tag? No, we don't. The item itself is designed for parallel access, so within a single Runspace concurrent dictionary or concurrent queue, we don't have any access problems. And the other part, which made the whole thing possible, is that we only check the status if we no longer got anything from the queue. So if we first queue the last item and then set the status, in that case, the subsequent worker cannot hit this position unless it dequeued that item correctly. Hypothetically, we could actually have a race condition. However, that would require that I manage to do both of these steps in that in between those two steps, the other Runspace managed to do both of them at the same time. And that's statistically not probable from a processing cost perspective. It's not 100% guaranteed, yes. You would need to, you could add an explicit sleep in there to ensure that. Otherwise, the alternative to that is that we build our own class that with a lock that makes both actions a safe transactional setting, and in which case we could avoid that. In fact, that is more or less what I did with my custom queues with the closed flag. What's happening behind the scenes, I have created my own custom concurrent queue, which inherits from the native concurrent queue, and added additional properties, including the state of whether it's closed or not, and whether it's how many items have ever been added to it. So I can do the tracking properly. And in those cases, I overrode the default methods to ensure the scheduler. Well, if nobody's got any more questions, thank you for coming. You know where to find me if you have any follow-up thoughts, questions, opinions, feedback, or want to talk about anything else PowerShell. I think I've well established that it's a lot easier to get me started than stop talking about it. Thank you, everybody, and looking forward to later.